in the context of mechanisms with money, we have discussed one important class of mechanisms called the gross class of mechanisms. And one special mechanism in that class is called the VCG mechanism, which we have discussed in certain detail. Now, even though these two classes, so essentially both the gross class of mechanisms and VCG, both implement the same allocation rule, which is the efficient allocation rule. Now, in this module, we are going to generalize that allocation rule to incorporate a larger class of DSIC mechanisms that also lives in the quasi-linear domain. So in some context, you might be interested in finding a larger class of mechanisms which are also DSIC, and we might not always be needing the efficient allocation rule. So how we can actually incorporate that? So this class of mechanisms, which is a larger class than the gross class or the VCG class of mechanisms, is known as the Affine Maximizer. So why is it called Affine Maximizer? So in this rule, every agent has a specific weight. So here by Wi, we are denoting the weight of player I. Now we are multiplying that weight with the valuation of this player. So you can actually interpret this number as the valuation of player I when the allocation decision is A and his type is theta I. We are just using the shorthand because type itself is the valuation for this player. Now we are taking the sum over all the players of the weighted sum of all these players, and then we are applying a translation function which is denoted by kappa. So this kappa is a function of the allocation, so it maps the allocation space into the space of real numbers, and it can be any arbitrary function. So this is what we are going to call as a translation, and this is the just the weighted sum. So together they constitute one affine sum of all these players' valuations, and therefore the name Affine Maximizer comes in. We are trying to maximize this affine sum with respect to the allocation. So picking the allocation that maximizes this affine sum, and therefore it is called the Affine Maximizer allocation rule. Now if you notice carefully, this is clearly a generalization of several things that we have discussed in the past. So the most common thing is when you have this kappa A, so this function is identically equal to 0, and all these weights Wi's are equal to 1. So this is one special case where you get back the original efficient allocation. Remember that we had this allocation summation over theta i's, and if you are picking the argmax with respect to A in A, that is essentially the efficient rule, which is implemented by the VCG mechanism and the gross class of mechanisms. So this is one special case of the Affine Maximizer rule. The other one is if you just pick WD, so there is a distinguished player which we call the dictator. His or her weight is essentially 1, and for all the other players the weight is 0. So you just look at the valuation of player I and pick the action, pick the allocation that maximizes that valuation. So you are only making the dictator happy and nobody else. So, and also kappa is identically equal to 0. So both efficient and dictatorial rules are special cases of the Affine Maximizer rule. So this is clearly a superclass. Now we immediately notice that something we have broken the VCG mechanism to this mechanism called the Affine Maximizers. So when you have these weights which are different, then this allocation rule is not anonymous. Quite clearly, if you have, let's say, W1 and W2 which are different, when you swap these two players, their identities just get exchanged and their valuations remain the same, because W1 is associated with player 1. So therefore in the new game, this weight will be placed on the valuation of the new player 1, which was player 2's valuation in the previous game. So therefore the allocation might change, so therefore it is not anonymous. The other thing to observe is that this kappa function could be a non-constant function. So it may have different values for different allocations. So it means that it is giving different importance to different allocations. So this is something which is known as non-neutral, something that we may not discuss here, but imagine a property very similar to anonymity, where agent identities do not matter. So anonymity says that the players can be renamed, but the outcome should not change. Similarly, there is a property called the neutrality, which says even if you alter the alternatives, or the allocations, the outcome should not be changed, or it should change in a consistent manner. But because of the introduction of this kappa of A, that property is getting violated. So that's not super important at this point, but let us just keep that in mind. So we have already seen that it's a affine maximizer is a superclass of this efficient allocation rule. So it is expected to satisfy more properties. So one implication of going to this larger class is that we'll see a characterization result which is very similar to the GS theorem in the context of quasi-linear preferences, that we can actually characterize a bunch of properties, DSIC being one of them, to this class of mechanisms which are known as the affine maximizers. We'll get to that in a moment. Now we are going to also assume one property of the affine maximizer rule. We are going to call this property as independence of non-influential agents. So INA for short, non-influential. So what does it mean? So suppose there exists a player whose weight is 0. Affine maximizer works with these weights. This weight is 0 for that player. Then what this property is saying is that that particular player should not be able to change the outcome by reporting any of the types, be it theta I or theta I prime. So for all those cases, the outcome should be the same. And that is why we are saying that this individual is non-influential. Now, how to make sense of it? Let us look at an example. So this just to make a remark that this is a tie-breaking requirement. So suppose let's look at this example. So suppose there exists a tie. So even though Wi is equal to 0, for the other players there is a tie. So the affine sum is equal for one allocation, let's say A1, and another allocation A2. Now the rule has to specify. Affine maximizer is just a class. The specific rule has to specify how it is going to break the tie. If you are going to break the tie by looking at, let's for our example, it is picking the allocation which is the less preferred one. So between A1 and A2, let's say this player I, who has a weight of equal to 0, he prefers A1 less than A2, but the outcome in that tie-breaking rule is A1. Then what can happen is this agent is definitely going to misreport, because between A1 and A2 he prefers A2 more, so therefore he will flip this alternatives or misreport its valuation, and that will be the outcome. So even though it's a very delicate point, but it is good to remember that we should not be doing this kind of tie breaking by looking at an agent whose weight is 0. So that is precisely the point. And this property that we have just discussed, that independence of in non-influential agents, this property actually rules out that possibility. It says that whenever this that player who has a weight of 0, no matter whatever his type is, the outcome is not going to change. Now we can actually state an important result, which says that this affine maximizer rule, which also satisfies this property of INA, is implementable in dominant strategies. And this is very similar to the result that we have proved for Gross class of mechanisms, and of course for VCG. And we are not going into the details of the proof, because the proof essentially depends only on the construction of the payment function. So we are already given the f of affine maximizer, the affine maximizer allocation rule, And the payment function is something that we need to construct such that this tuple FAM comma P of AM is DSIC. Now here is the construction. What it is essentially doing is it is dividing with respect to that weight of that player, and taking a very similar structure. If you look at it, it's a very similar structure to the gross class of payments. The only thing is the second part of this payment function, which was just sum over the theta I, theta j, f of efficient of theta in the case of gross payments, and j is not equal to I. This has been replaced by this function, and the purpose is very clear. I mean, once you have take the difference between the type or the valuation of player I from this payment, will essentially be able to prove that this is a mechanism which is dominant strategy incentive compatible. Now this expression of the payment is for the cases for all those players whose WIs are positive. So they have some positive influence on this game. If it is 0, if there exists a player whose WI is equal to 0, then the payment will also be equal to 0. So that's the structure of the payment. Now what we can do is we can show that this mechanism is essentially dominant strategy incentive compatible. And this also proceeds in the very similar way we have proved the gross class of the DSIC property of gross class. Just take the difference between the type at that allocation minus the payment at that allocation, and now you can see, if you reorganize it carefully, now this sum will be over j in n, and this is coming just because we have chosen it in a specific form, this form. So I just skip those steps. If you reorganize, you'll get this, and the last term is not dependent on theta I. So what we can observe is that when this theta I, so because by definition f of am is maximizing this sum, this affine sum, which is within this blue brackets, if you look at any other alternative, this is always going to be larger than that. And in particular, if you pick theta I prime, then also it is going to be larger than that. So therefore this inequality holds, and you can reorganize this term again to write that this is the payoff of player I when he is misreporting his type to theta I prime. Now this is for the case where for the player whose WI is positive. Now we'll also have to take care of the case where WI is 0, but then we know that the payments are 0 and the allocation does not change by the property of INA. So this property is due to INA, independence of non-influential agents. Therefore the payoffs are going to be identical for all types of player I, and that makes it weakly truthful. Player I will be weakly truthful in revealing its type. So that essentially completes the proof. Now, as we said that we are going to state a theorem which is a characterization theorem like the Gilbert-Southern. So we are going to consider the class of valuations which is unrestricted, and this is quite similar to the requirements of this GS theorem, which also says that you have all possible preferences over those M alternatives feasible in your type. So here what we are going to say is that this type function or the valuation function, which maps the allocations into real numbers, the space of all such valuation function has no restriction on it. So there is no additional restriction. It can be any function, right? And that's the reason why it is called the unrestricted space of valuations. In this space, we can actually characterize the class of DSIC mechanisms in the quasi-linear domain. And this result is due to Roberts, 1979. Notice that it also has a very similar condition. So if there are at least 3 alternatives, 3 allocations in this space, the original Roberts theorem is given for the finite number of allocations, even though it has later been extended for infinite spaces also. Then the other requirement is this type space is unrestricted. This is something that we have just discussed. Then we can say that every onto and DSIC allocation rule must be an affine maximizer. So this is a very strong result. This is saying that the previous theorem that we have just proved is saying that affine maximizer with this property of INA can be dominant strategy incentive compatible. But it is saying the other way around. It is saying that if you look at any onto and dominant strategy incentive compatible allocation rule, then it must necessarily be an affine maximizer. And that's a kind of a necessary condition. So still we cannot say it is if and only if, because affine maximizer is still a class, and this theorem can only show that it belongs to that class. And the INA property, the implementability critically depends on that INA property. So the reverse direction also requires INA. So we cannot really say this to be if and only if. If you just want to compare this with the GS theorem, it was restricting the whole class of mechanisms to dictatorships. Here it is restricting to affine maximizers. Of course, you can also ask very similar questions that we asked in the context of GS theorem, how we can restrict our attention to certain subclasses or subdomains, and then find some positive results. So do there exist some mechanisms which are non-affine maximizers or larger than affine maximizers in a smaller domain, restricted domain? And these are essentially open research questions. Some of these are already solved, some of them are not yet solved. So we will not go into the proof of Roberts' theorem. It's really very long. But if you are interested, there is a very nice paper by Lavi, Mualem, and Nissan. The title is also Two Simplified Proofs. They provide two proofs of the Roberts theorem, and both are really easy to follow. So an interested reader, you can take a look at this paper.